All right, so since the network is deciding to be really slow, we're going to go ahead and just skip to over GNU plot for now and go to real quickly perf and then timing. Although I just realized we need to do this the other way around, so let's go to timing. All right, so timing, empirical measurement. We want to be able to come up with some empirical measurement of our program. So we need to come up, we need to come up with a way to capture time. This is actually an incredibly complicated topic. Trying to figure out how, determine how long something takes on your machine. It is incredibly complicated, but we're going to go with the naive, simple way of we start recording time, we run our code, we record the end time, and then we subtract the two. Seems like that should be the best way to do it. The problem is recording start time takes time. When you're running it, something else may happen to your machine that you were not aware of, and then when you're trying to record it at the end, you're taking up time as well. And then but number 4 so far has been good. We haven't messed that one up yet. But the other 3 are not good assumptions. But for this course, we can just assume those 4 things and we'll be good to go. All right, we could go and read code here, or we could just jump over here and go ahead and look at our timing template. And I think this will be a little easier. I went ahead and wrote this out for y'all just to make it a little easier so you can just copy and paste. That way I don't have to type it out as well. So here's a program to do some basic timing. You have main. The clock T is what C uses in order to record time, or is a method for recording time. And I'm going to create 2 variables of clock T, one called start, the other is diff, aka the difference from end to start. And then we'll have a double so we can actually represent how many seconds have elapsed. Now, ignore the for loop for now. We're going to start the clock by capturing, so start equals clock. That's how you figure out the start time. We call our function, aka what we want to do. And then we create the diff by getting clock, aka what the clock is now, minus what our start time is, so that's the diff. But this diff is stored in clock T, not stored in seconds. It's actually stored in number of processor cycles that have gone by. aka you're on a 4 gigahertz machine, you have 4 billion cycles per second. So it's really recording the number of cycles. So we need to convert that number from cycles to seconds so we can actually understand what's going on. Simple way to do that, take diff. You multiply it by 1.0, that makes diff a double. So now we can do a division and not have our truncation happening. And then there's a constant called clocks per second, how many clock ticks happen per second, and then that will give you the actual time, and then we can print it out. Okay. Oh yes, so we print it out, and then don't forget to flush, because if you don't flush, then it will not print out what the last timing was. So you have to flush it, otherwise it will store this inside an internal buffer and not actually print it out to a file. What?
Just thinking it belongs to the toilet, so that's why we're flushing it.
Look, I can't tell you how many programmers forget to flush, okay? All right. So let's do let's go ahead and make an 04. Let's see, timing examples. CP timing template to here. Actually, let's move timing template to sums test.cpp. All right, so I just copied over. Here's our code again. Let's go and create an imp sum to n. Int sum equals 0 for int I equals 0. I is less than n. Probably should tell what n is. Sum plus equals I, return sum. All right, what's the big O of this?
Yes, and
It's in, right, it's in. Simple, hopefully simple function. By the way, is there a faster way to do this? Yes. This can be done in O of 1 time, but I'm doing it in O of n just to show a point. All right. So the function to call your algorithm is we're going to do sum, and that's what we're going to get the timings of. Now, why do I have the for loop? Well, now when you go and try and get timings, you need to figure out what range you want to have in and then what steps in order to get valuable information. When you do this timing lab, this is what you're probably going to spend a good amount of time is trying to figure out what values I should be. And when you do timings yourself, that's what you need to work on. So I have it start at 1,000 because, I mean, if I try and get the sum from 1 to 1, it's not going to be very useful. So I want to start at 1,000. What do I go up here? 3 to 1,000,000, each time incrementing by 1,000. And then I'm going to print it off down here. That looks great. Let's go ahead and, can we compile it? Hey, it ran. Okay, so it's printing out, this is the I, aka the size of n, and how long it took. Now, I'm going to tell you right now, if your value is below 0.01, it's very hard to get accurate numbers. Notice that these numbers are jumping around a lot. So you need to make sure that I is big enough so you get a value that's actually meaningful. Because this number should take longer, or should take less time than what's larger, even though that's not what's happening. That's because, like I said, there are a lot of, there's many different things that can affect these numbers on the small scale. So you need to make sure I is big enough so you capture on the greater scale what's going on. So let's go back into sums. And hold on, let's go and jump up an order of magnitude. So we're just going to have I start there, put in a 0 there, and a 0 there. All right, let's do it now. Okay, that's starting to look a little better. Still getting a little jitter, but not too much. So let's go ahead and we'll bump it up one more time. And we're going to leave that one there. That way it starts off large and doesn't take as long. There we go. Oh, good. Oh, great. So now we actually have some numbers. All right, so this, I would say, is the minimal level of what's acceptable. You do want to take a little longer, but when you're starting out, you're just trying to get it to work, so you don't want it to take too long. But we'll stick with this for now. Let me see if it's installed yet. Nope, still going. Okay. When you run it, you can dump it. I usually call it data.dat. Remember that whole greater than sign in order to take the output and dump it to a file. Then you can open it up and look at all the numbers here. All right, and then once GNU plot comes back up, I can show you how to take those numbers and then quickly generate a plot, if that ever happens. All right, so this is where I was telling you the number's too small, so you must increase the I. Okay, if I were to plot it, when GNU plot comes back up, it would probably look something like this, which that's a linear graph. Notice that for the most part, it's just going up straight. All this jump, remember that's when I was telling you there can be extra things going on. For example, maybe at this point, someone logged into the machine, or you got a bunch of network packets or something. Little things can affect it, but if you look at it from a general perspective, it looks okay. With GNU plot, you can actually plot two separate lines. If I get that installed, I can show you. So you can compare one, hey, here's a red one versus a green one. Oh, I did something funny right here. So from here, you can tell which one's faster, aka lower is better, because on our x-axis, we have the size of I, and on the y-axis, we have how much time it took. So obviously, the red one is faster than the green one. Okay. Now let's go ahead and look at sums, and let's do, actually we're going to do this. Let's do super sum. Okay. Hey, what's the big O of this? Ooh, I have a function in a function. Oh no. I just realized this is not going to compile. Oh, actually, no, it might. It might compile. Let's see if it compiles. Yeah, I didn't think so. Because it can't be a function right there. Super sum. Now it should compile.
No, you don't have
forgot
a semicolon. Yeah.
Whatever. Semicolons. Alright, there we go. Okay. So what's the big O of super sum? Well, it's calling sum. So that means it has to be at least the big O of sum. So what's the big O of sum? Yeah, O of n. So then how many times does super sum call sum? N times. So super sum therefore is big O of n squared. All right.
That's one of those.
It's one of those. It's the n squared one. So we'll go down here and let's change it to super sum. It takes a lot. Oh. Yeah, by the way, n squared is way, way slower. So we're going to have to knock this down a bit. And by a bit, I mean a lot. There we go. Wow.
Just brought the computer screaming, "What are you doing to me?"
Why? Notice that in order to get numbers here, I had to manipulate I again. Do not be afraid to manipulate I in order to figure out the range, in order to just get some numbers. So obviously, it's going to be a pretty radical difference.
Well, we're getting numbers, all right.
We are getting numbers, see? It'll compile, it'll finish eventually.
There's a 3.
3.3. 3.6. Okay. Did this ever finish? Oh my goodness. I love how it says 100%. By the way, that bar, you know, in Windows where it says 100%, that line never ends. It's everywhere. Okay. Well, so do we have perf? We don't have perf. Wow. Okay, well, looks like CSU has betrayed me today. But that's all right. So we're going to move on, and I guess we'll have to get back to this lab, hopefully today. So you can analyze, we'll go ahead and summarize then. You can see that we can analyze an algorithm analytically, predict performance. We can then profile the code or run it with timings to get the empirical numbers. And hopefully, if I was able to show you, you can see that the numbers actually are the same. By the way, I could do a whole class on performance analysis, but we're just going to stick to the basics, basically what we learned today. But I do want to alert you to a couple of things that will get you. If you plot the data of 2 algorithms, but you only see one, what do you think happened?
They're the same.
It could be the same. What are the chances of each one of them doing this? I'll just say practically 0. But that's a good guess. Good guess. If I did those 2 that I just showed you today, notice that the time goes from 0 to 0.003. Where's the green line going to be? Right. So it's going to be basically that. You can't see it because the difference is too huge. And this may happen. You got to adjust your axis so it goes from here 0 to 2. There's the green line, and then there's the red line. In other words, in this situation, the algorithms are so different, it's hard to even see them on the graph. That may happen, so keep that in mind. And that's the code to do it. Another thing, once we get perf up and running, wow. Perf is going to tell you, will profile your code in order to tell you what's taking up the most time. Oh, you can't see that red. That's a nice dark red. When you run your program, you might have a function like sum or super sum. I'm just changing, actually this one would be super sum and that one would be sum. Notice that regular sum took 0.2% and then super sum was 95% or sum to 1. That means that if you want to increase the performance of your code, you should focus on the function that's taking up all the time, not some other function. And perf is going to give you that information for you. All right. There's a lot. I know I threw a lot at you, and I wasn't able to do some of it because of the network, but we'll get to that hopefully today. We did do an analytical deduction. That's great. We haven't been able to profile it yet. We'll hopefully get to that. But we want to be able to empirically run. We were able to empirically run and get performance numbers. We just were not able to plot them yet. So there are some abnormalities here that aren't going to be addressed in this class, but we will get to them. I mean, you will get to them in architecture and operating systems. Any questions? Yes, I can't assign this lab yet.
Do we need perf for the lab?